So here we go. So now the only thing you need to understand here is this. So there is PFC was created and we started selling it in 1994. And it got to be about 2010, which is 16 years later, and software gets out of date pretty quickly nowadays because operating systems change. And also computer languages evolve. And so in 2010, we decided that the PFC code itself needed to be recreated using modern technology. And so that was a big effort. We spent 4 years doing that, and we ended up creating PFC version 5. Okay. And so I, for fun, used to call that PFC 5.0 because version 5. Okay. Now there is and so I said, geez, we're doing this big development, PFC 5.0. We need to have a song that goes along with PFC 5.0, something that's like really cool, real sexy. Everybody thinks it's neat. So there is such a song. You're going to hear it now. There is a television show in America called Hawaii 5.0. Do you know what Hawaii is?
Yeah, of course.
What's Hawaii?
That island in the ocean.
Correct. It's in the ocean, and it's an American state. So everybody in America certainly knows about Hawaii, okay? And it's a real kind of cool place because it's warm all the time, and everybody in Hawaii looks really good. They go swimming all the time. They have tans. And so the television show is about these detectives, and it's like police. And so there's a special police unit, and they're the 5.0 police unit, District 5. So it's Hawaii 5.0, okay? So PFC 5.0, Hawaii 5.0, and we're going to show you some cool stuff about PFC. We're going to show you like this, for example. Can you tell what this is? This is where you put coffee beans into the grinder. It falls in here, and a grinder grinds them up and makes you coffee.
Okay.
Right? So this is something you can model PFC, right? Okay, here we go. Tell me if you can hear this. Can you hear it?
Oh yeah, we can hear it. Yeah. Oh my God, this song.
I love this song.
We know this song.
There you go. Thank you very much. So, PFC. So lest you think it's all just fun and games, which it clearly is, it's very fun to do things with PFC. This is an example of all the different research. It's mainly being used by people doing research. Most of them are at universities. Some of them are at large companies that have research groups. And so this is, as you can see, this is an example of the number of research papers that have been published each year. And this is not cumulative. So, in 2020, there were 200 papers published. In 2023, there were an additional 280. And then this is a breakdown of the numbers. And this is probably not even correct because it's probably too low, because this was just some stuff we did some years ago. One of the guys who used to do PFC would always keep track of this in some general way. So PFC actually is used to do science. And as you also know a little bit now, it was developed actually 79 when Peter published his paper, and it was used for granular material. And now We use it for solid material because if you glue it and when it breaks up, it turns back into granular material. And this is a quote since we're in the rock mechanics world here. And so this is from a paper by Ted Brown and Everett Hook and Derek Martin in 2014. They were looking at, it was a whole big review of all this work related to modeling fracture in rock. And I kind of love this. This is a really good quote that sums everything up about bonded particle modeling, right? The development of the bonded particle model based on PFC2D and PFC3D. These were codes by Peter Kundal and his co-workers at Itasca, represents one of the most significant contributions made to modern rock mechanics research. Notice they're talking about rock mechanics research. And why is it useful for research? Because of what's in blue here. This model can reproduce the essential features of the initiation and propagation of fracturing. And notice that they say the essential features and also subtle features. There are sometimes things we learn when we carefully build PFC models to test our hypotheses about rock fracture that we had never thought of before. And so also it talks about rocks and rock masses. So not only do people look at like individual small specimens of rock that are typically going to be free of initial fractures, people also apply this at the rock mass scale. So now you have an entire big tunnel, and you want to look at the damage that forms in the roof of the tunnel, for example. And when you do that, you cannot model, the PFC particle has to be bigger than the grain of the rock. And so this then is a very interesting issue because if you take a specimen of rock that's only, 50 millimeter height and 25 millimeter diameter, that's a typical specimen, and you do all sorts of laboratory compression and tension testing, you can measure the response and you come up with properties. What's the Young's modulus? What's the unconfined compressive strength? What's the tensile strength, right?
Yeah.
If you then, and so you can do the same thing with PFC. That's what we do. We build models at that size so that the particles are about the same size as the grains. And then we can choose the micro properties so that we can match the stress strain curves from those laboratory tests. Okay?
Yeah.
And we call that process calibration. It means taking your model and changing its parameters in such a way that it matches some sort of important macroscopic thing.
Okay.
And so we can do these things, and we can do them with various types of contact models. However, let's say we do that. Then if we take that same exact PFC bonded particle model with the exact same properties, and if the only thing we do is make all the particles 50, let's say 100 times bigger, because now we need to represent a big hunk of a tunnel, of the roof of a tunnel. So we have to make all the particles bigger, but we keep all the micro properties the same. What we will find is that the synthetic PFC material will be too strong. It will be too strong. And so we then have to somehow reduce the properties, reduce the stiffness, reduce the strength.
Okay.
And we can do that, and we can eventually reduce it until the point where we start to get failure, just like in the real world.
Okay.
But the process of how do you reduce those things is not fully understood. That's an area of active research.
Okay.
Because if you want to make a quantitative prediction, if you want to go to a new tunnel somewhere, well, you have data of laboratory tests for that tunnel. You could build a model that matches the laboratory test, but I already said it's not going to work to predict failure in the tunnel, and you have to reduce them. But how much do you reduce them? You need to be able to know that at the beginning so that you have a procedure that allows you to predict things. So that's an open area of research. It's similar to what occurs in reality. When you build large models of a rock mass, people talk about the fact that at the scale of a rock mass, the material is weaker.
Mm-hmm.
And they talk about this. They say, well, if you have an intact small hunk of rock, it's really strong. But if you take a bigger sampling, now you start to get joints and you start to get other areas of weakness, because when you take your intact rock, you've selected like the best part. And so this is a real thing too. This is I don't know what you want to call it, scale effect. Just by taking the scale, the amount of material, making it bigger, you start getting these other things in there that end up degrading its properties. And so this is really happening as well. And so that's why this is an interesting aspect of research, because there's something similar with the model and with reality. And so, this would actually be the big, broad picture of the kind of research that I'm continuing to pursue. Okay. So if you were my PhD student, that would be kind of the sorts of thing that I would turn you loose on. So we'll see. And I'm trying to kind of influence you here so that when you sit down with Frank and you guys try to figure out what you're going to do for your research, you can maybe say, hey, this scale effect thing is really interesting.
Okay,
does that make sense?
Yeah, of course.
Okay, good enough for now. So now, another quick side thing. Did you get a chance to read the Starfield-Kundal paper?
Yeah, of course. I read both of the two papers, both about how to think about the questions and the basic information about DEM.
Okay, what did you think? They make sense?
Yeah, of course. Well, there's one thing that I am consider about it, that is about the delta t, which is time step. We should make it very small, that between the time step, I forgot how does he say that in the paper. So I think my mainly question is that how can we know how the time step will be?
Got it. We will talk about that today.
Okay.
That's, again, what I think is fundamentally important for someone who's going to be using the code, especially doing research with it. The quick answer, there should always be a quick answer, because the basic idea is always simple of everything. So the quick answer is this. Pretend that you're sitting at some table, right? Is there a table in front of you that you put your hands on? Okay. Put your hands on the table lightly. Okay. Now, pretend that I am sitting at the other side of the table facing you. Okay. Now, keep your hands there. Now, if I take my hands and if I smash the table, are you going to be able to tell?
Yeah, of course.
With your hands?
It will. Yeah, I think so.
How? What will you feel?
Because it will shake, not shake, but
correct. Shake, vibrate.
In Chinese. Yeah.
I'm sorry, what'd you say?
I said a word that 震动. Maybe I need Shihang to
Shihang,
translate
help
it.
us.
Is that shake?
I think so. Shihong, what's she trying to
Yeah, yeah.
say?
It's the shake. It's all the vibration. The shake. The shake. I think it's
Yeah,
the
so vibrate would be shake back and
yeah,
forth. That would be the shake, right?
yeah.
Okay.
Yeah.
Mm.
So let's talk. So that is correct. Okay, so you would hear two things. You would hear the sound, right? And the
Mhm.
reason you hear the sound is because there's compression going through the air, which your
Yeah.
eardrums are catching. So that's also a vibration, right?
Okay. Yeah.
But in addition, when I hit a solid body, there is a wave that propagates through the body. Think of it
Mhm.
as I hit something and this little part of it starts getting pushed, which then pushes the next part, which pushes, and this wave spreads out. Okay. And it takes a
Okay.
finite amount of time in a real system for that wave to move. Okay. And so
Yeah.
there is a
Of course.
lag. If you could measure carefully the time when I hit the table, it's going to be a little bit later when you feel it. Okay.
Yeah. Yeah. Yeah.
So
Yeah. Of
there is,
course.
we call this a wave speed. And it turns out that the wave speed is related to the Young's modulus and the density of the material.
Okay.
Okay.
Yeah.
And let's keep talking about that. If the density is really low, the wave speed is fast. Okay. If it's, sorry,
Okay.
I'm trying to remember this. It's
If
E over rho.
mhm.
Density is high density. It's slow. Let's not worry about this. Um, let's forget about the density. Let's talk about the E, the Young's modulus. I believe that the wave speed is proportional to the square root of Young's modulus divided by density. Okay.
Okay.
Young's modulus is a measure of stiffness. If the material is very soft, very low
Mhm.
Young's modulus, that means the wave
Mhm.
speed is going to be low
Yeah.
because it's E over rho. Okay. And
Okay.
if E is very, very stiff, wave's going to go faster.
Yeah. Yeah.
Okay. You could sort of
Okay.
think of this, right? If we make that table into some very, very, very soft, rubbery material, it's going to take longer for that wave to go across. Okay. So
Okay.
what we've established so far is that for a real body in the physical world, we can relate the wave speed to the stiffness of the body. Okay.
Mhm. Yeah.
Okay.
Yeah.
Now, think of a PFC model. A PFC model is a collection of masses that are connected with springs. If you remember, I had that. Oh, I haven't shown you this. We'll see this later. But it's a collection of masses connected with springs. Now, think of a simple system where I have a mass. Think of it as like a ball, and then a spring, and then a mass, and then a spring. So think of like 10 of those. Okay.
Okay. Okay.
Now, if I take it on here and if I smash it, so I apply a big pulse of velocity,
Mhm. Mhm.
think of what's going to happen. It initially you don't know anything over here. It's going to
Yeah.
take a finite amount of time till the information reaches this. You can think of it that way. So what
Yeah.
happens? This thing starts to move, which pushes this spring, which causes force to start to act on the second guy. And that
Yeah. Of
force
course.
then makes this guy start to move, which pushes this spring, and there's a chain reaction. Okay.
Yeah. Yeah. Yeah.
Now, because of the way we're doing the distinct element method, at any given point, we know all the information. We know the velocities and positions and masses. And now we want to predict what's going to happen at a certain time ahead of us, right? Now,
Yeah.
you can think of it as that time step needs to be small enough so that when I move this, it only affects those springs. It's
Okay.
local. If instead because when I move this, I have to update the total force on this guy. Now, if the time step was really big, when I move this, it's affected by everything over here.
Yeah, of course.
Which means I can't then just take one step to update these forces. Then it gets more complicated. So the time step has to be small enough that information cannot propagate further than one layer of springs. Okay. And that's physically related to the wave speed in the material. And the wave speed is related to Young's modulus over density. So if you increase Young's modulus, the wave speed is faster, which means the time step has to be slower. Okay. And the equivalent of Young's modulus for our system, here's the ball, is this cage of springs. The result is it's like a Young's modulus. It's a stiffness that resists motion of this mass. Okay. So that's what happens. That's how the time step is going to be selected. Okay. It's going to be related to the stiffness. Each mass is surrounded by springs. So it has an effective stiffness. It's not just one spring, because there might be 6 of them. So when I go like this, I stretch these other springs and I push this. So it's like an effective, you can think of it as one effective stiffness. And so if that effective stiffness gets higher, it's more stiff, wave speed is faster, time step has to get smaller. So, so if you increase the stiffness in the model, the time step gets smaller because of this information propagation business. And conversely, also, if you increase the mass, that actually slows the wave speed. So the time step could get bigger because it's E over rho. It's Young's modulus over density. And in the discrete system, density is related to mass of that spring. Are you with me? Are you with me?
Yeah. I got you.
One other way of thinking of this, think of that mass somewhere inside a packing of other masses. So this mass, the only thing this mass knows is that he has 6 springs that are each giving him a force. That mass knows absolutely nothing about what's happening 6 layers away. And it never knows that. It only knows all the time, it only knows its local environment. And so think of now this whole big system, everything's in static equilibrium, so nothing is moving. Everything's in perfect balance. This guy has, 6 forces, but they all sum up to 0, so there's no acceleration. Just sits there. Now, think if I could go in there and take that mass, just that one, and I could pull it and let it go. It would start vibrating back and forth. Do you agree? And if we plotted its position, let's see, position versus time, it would look like a sine wave. It would go forward, backward, forward. So we could, and that would be a frequency. That's a period. I mean, the amount of time it takes to go one cycle is a period, is the period. That system is a mass and effective spring, and you can solve the differential equation for a single mass and a single spring, let it go, and it goes like a sine. And you may have even done this in introductory physics. And what you will find for that system, there's only 2 parameters in that system. There's the value of the mass and there's the stiffness of the spring. And what you will find is that the period, the amount of time it takes to shake back and forth, is related to the square root of the mass of the stiffness over the mass. And so the stiffer the system is, the faster it vibrates. And similarly, if you make the mass bigger, it vibrates slower. And so now think of this, that you're tracing the motion, again, that plot, delta on the y-axis, time on the x-axis, it's a sine wave, right? Now, we know the value at some point. That's our current point in the model. We know the value. Now the
Mhm.
solution is it's going to go down and it's going to go up, and we need to like here's a dot. Now we need to get to the next dot. Now we need to get to the next dot. And you can work out that there's a certain number of times that you have to sample over one period in order to be able to still extrapolate and make these approximate solutions to stay on the curve. Okay.
Yeah.
And that can all be done theoretically and stuff. It turns out to be something like about 4. Okay. 4 times you have to sample. Well, notice those 4 times, that's the time step, because this is the t-axis, the time axis, and you have to sample it here, 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 and here. So if you know the period of that one guy, you have to take that period and divide it by 4, and your time step has to be that size or smaller.
Okay.
Okay. Because remember that this is critical time steps. So if you make time steps smaller, you don't affect anything. You're still getting the correct solution path. But if you make it bigger, now when you extrapolate forward, you're going to be getting it's some meaningless thing. And then that's going to feed back and you're going to get more meaningless, and your whole entire model will blow up, meaning that suddenly the positions of the particles will be e to the 26 somewhere. Okay. So this is the idea. And notice that that period of that single mass, again, is related to square root of stiffness over mass. Increase the stiffness, it gets, mass over, if you increase the stiffness, it goes, it goes faster. I got it flipped over. Right? If you, a stiffer system vibrates faster. Okay.
Yeah.
Okay. So again, so the end result of all this is that, and so what we do in PFC is we go to every single time step. So we know the state of the system. PFC has to make an estimate of what the new time step is. And so how does it do that? So what it does is it goes to each mass, it computes the effective stiffness of all those springs, and it knows the mass, and it takes square root of k over m, and that's its approximation of the time step. And then it does that for this mass and for this mass, and they each give an approximate answer, and then it takes the lowest of all those. Okay. And so what ends up happening then is that the stiffness of the system, if it's moving around and change and stuff, the stiffness can actually change, which means the time step as you run the model will slightly change.
Yeah.
Okay. If you don't have a sophisticated algorithm like this, then what all that people can do is they have a single number time step, and they say, fix the time step at this. And then they run their model and it blows up, and they say, oh, no good. Fix the time step half that. Run the model. Oh, it's okay. But of course, that's not very efficient, because they're probably making it too small than it has to be. Okay.
Yeah.
So this is the overall thing. And so, for example, if you have a PFC model of a collection of sand in a cylinder, and you drop it, you start here with the sand, you let it fall, and it forms a pile. Okay. And it just sits there. You keep cycling and everything, nothing is changing. It's static equilibrium. Great. And so based on the mass and stiffness, as I said, it's going to have a time step. And you can run PFC and you'll see the time step is a certain number. Okay. Now, so for example, in that system, if you now suddenly just change all the masses, make them bigger. Okay. Oh, wow. You change the mass. The frequency is going to be slower. Oh, the time step will automatically get bigger. Okay. Or conversely, if you take that system and you magically now change all the stiffnesses, if you make it stiffer, time step will get smaller. Okay. And you can do this. And then here's the secondary, more interesting thing. That's kind of obvious. If you change the properties, you're going to change the time step, but usually you don't change the properties, right? If you want it to be a real sand, It has a
Yeah.
stiffness. It has a mass.
Yeah.
It's formed a pile. Okay. But now you might take a piston, a steel platen, and you might slowly push it down into this sand. And as you push it down, you measure force on the platen and you measure displacement. And so you plot force on the y-axis, displacement. And what you find is it starts off, you know, when it's not touching, it's just 0. And then it starts to ramp up and it stiffens. And then it's kind of linear. Okay.
Yeah.
This is actually
I
a
can
test
try
that
it.
they do. They call it an odometer test. At least in soil mechanics, they call it an odometer test.
Okay.
In other areas, they call it a uniaxial strain test, where you're straining it, but the sides don't expand. Okay.
Okay.
Such a test, if you model it with PFC, so it's not touching, so there's a certain time step. As you start to compress the material, okay, what happens? I'm one of those guys inside there with 6 springs around me. That means I have 6 contact points. Okay. Now, when I start to get compressed, all of the packing gets more dense because I'm pushing down and it's not allowed to expand.
Yeah.
So I got the same amount of material, but it's getting less porous because I'm forcing it to compact. Now, what you will find is for a typical grain in there, it started off with 6 contact points, but now I compress it. Now, now it's got 7. Because now there might have been a place where it was really close, but it wasn't touching. But when I strain it, now there's a new spring. And now there's a new spring, okay? Which means that if you think of just that mass, remember there's an effective stiffness of all the springs. If I add more springs, I add more stiffness. So that mass will now vibrate faster, which means the time step's going to have to get smaller. And so we can see this. We're going to end up doing an odometer test, actually. And we're going to watch as we load, the time step is going to get smaller, going to automatically get a little bit smaller. Okay. And we also would be able to monitor something which is like average number of contacts per particle. That's actually a term called coordination number. In soil mechanics, people describe soil behavior in terms of coordination number. How many contacts on average do I have? And as you compress, if it can't expand, as you compress, you end up getting the coordination number gets a little bit higher. Okay. Does that make sense? Okay. And the last thing about that, remember I said when you do the test, you measure force on the platen on the y-axis, applied displacement on the x. And remember I said it starts off 0, and then it starts stiffening. Okay. What's happening? Why is it stiffening? What do you think?
Because at the beginning, the shape of the fan will be changed, so it won't be all pressed, but at the end of it, it will be like all the sand will be pressed. So it will be like this, and then keep like this.
You're on the right track. So in the world of structural analysis and things, you're plotting force and you're plotting displacement. And if you have a curve of force versus displacement, the slope of that curve is related to the slope of force displacement is the stiffness. That's what stiffness is. It's the ratio of force over displacement. And so notice as the slope increases, it's because the overall stiffness of the whole system, because it's the overall measurement. You're measuring the total force pushing for the whole system and the total response. It's getting stiffer. And it's getting stiffer because as we compress, there's more little springs. There's more surfaces coming into contact. And the more surfaces in contact, the stiffer the system is. Okay? So all of those things are going on. And that's why the time step is getting smaller.
Okay.
So the big picture, what's the basic idea? How do we get time step? You tell me.
So, well, it's about, maybe I would divide it into two parts. One is about the material. It's about the road, the young small model, and other things. And
the
then the
density,
other part,
correct?
yep, and the other part of it is about the contact, which means the springs. If the contact gets more, and the time step should be smaller. So I
Yes,
divide it into two parts.
yes. Think of it as each mass is surrounded by springs, and if I just disturbed it and let it bounce back and forth, it's going to bounce back and forth at a certain frequency. And the faster it bounces back and forth, the more I have to sample the system in order to trace the motion. And that's why the time step is related to how fast it bounces back and forth, which is related to the mass and the stiffness.
Okay.
So that's the idea. Okay.
Okay.
And so it's a very complex thing. There could be one part of the system where it's highly compressed, and therefore that controls the time step. The time step has to be small enough for the worst case part of the system. And so this is all going on. And what I'm saying is you can't figure this out in closed form before you run the model. That's why the model itself has this algorithm that's always adjusting the time step. Uh-oh, I think I've lost you. It's adjusting the time step as the simulation is running. Okay.
Am I still there?
Oh, are
I
you
can
still there?
hear you. Yeah, I'm still there.
We're back. Okay. All I was saying is, therefore, we can't figure this out in closed form before the simulation. We have to actually, as we run the simulation, in response to where it's getting compressed, the system has to keep making new guesses, new estimates of that critical time step. So that's why it's changing. Okay?
Okay.
Okay.
I got
Enough
that.
said. We'll cover that in the physics part. Now, here we go. Watch this. I am going to use the magic pencil here. Just a second. Share screen. Okay, now you tell me when. I assume you can see my screen now.
Yeah.
Okay.
Okay.
Let's talk about the big picture of where we're going today. So we're really going to talk about the physics. But once we're done with the physics, I want to describe to you the big roadmap of how we're going to learn this stuff. So we're going to have an example, and we're going to actually do this example together running PFC. Okay.
Okay.
And so what is this example? Let's call it this. Oops, hang on. My pencil is an electric pencil, so it has to get turned on. So we're gonna have a PFC project that we're gonna call Pile Up. Okay. And what are we gonna do? We're gonna take some region of space, like a box, and we're going to, so let's talk about this box. So since it's a region in space, it's a box, we have to have a coordinate system. We'll do it in 2D. To make it simple, we'll put the coordinate system at the center of the box, and we're going to generate a cloud of particles inside that box. Okay. This is, and we're not going to do this till later, but I want you to get the big picture. We're going to generate a cloud of particles in that box. We're going to have gravity acting the negative y direction, and we're going to make another box here, and I'll call this the bin. This is not going to move. So this is sitting here,
Okay.
right? And we're going to remove this wall, and we're going to let these things fall under gravity, and they're going to
Okay.
form a pile. You with me?
Yeah, of course.
Okay. This is
Okay.
the beginning point. Okay. And so we're going to talk about, for example, you know, build this whole model with the smallest number of PFC commands. Okay. And so one of the things we're going to have to talk about is the contact model. And we've only briefly talked about this, but don't worry, we'll talk more about it. The simplest one is called the linear model, and it has a normal stiffness, a shear stiffness, and a friction coefficient. Okay.
Okay.
And we're gonna make this really simple, and we're gonna put both of those equal to 0. So now our entire system only has one parameter, normal stiffness, right?
Yep.
Okay.
Yep.
And all we want to do here is form a pile. We don't really care about anything else. Okay. And we want to look at, like, how does this pile pack? And so we're going to choose the stiffness so that the overlap, the worst case, is going to be small relative to the size of the average particle. Okay. And because you can think of this, you're going to let this thing fall, and it's going to form a certain pile with a certain height, right?
Yep.
Now think of this. Let's say I had stiffness, and I put the same stiffness for, like, sand, really stiff. Sand is really stiff, right? The quartz grains.
Okay.
It's going to form a certain height, and that height will be just like the real sand. Okay. But for our purposes, let's just go, what if we took that system in equilibrium and we just made all the stiffnesses instantly 10 times less stiff? Okay. So if it's less stiff, this pile is going to move down.
Yep.
That makes sense? If it's less stiff, they settle more. Okay.
Yeah.
And also, if it's less stiff, that means, what about the time step? If we make the stiffness less, what does that do to the time step?
So it should be larger.
It's larger. For our case of doing a learning problem, we want the time step to be as fast as big as possible, so that it takes the smallest number of steps to get the answer. Okay, so that's why we don't care about the stiffness. But also, as the stiffness gets smaller, if I have two particles, they start off with a certain, there's actually an overlap here. And when the stiffness gets smaller, that overlap gets bigger.
Yeah.
Because the force acting here is the weight of the particle related to the gravity and the mass, right?
Yeah.
And so we want to make sure that this overlap is small relative to the radius particle. We are 5%. Does that make sense? Because if this overlap gets really, really giant, everything starts not making sense anymore.
Yeah.
Okay. So that's the initial system we're going to build. And as we do that, we need to learn all kinds of things. And for example, we need to say, oh, in the world of PFC, I create the particles. Okay. And then I have to say, take steps. So we call that cycle. Every time you do a cycle, that's one time step. Right? So then I could sit here and I could give a command, cycle 1000. And I could watch, and they would start to come down, and maybe they get like this far. And then I say again, cycle 1000, and they get farther. And I could keep on doing this till eventually they form a stable pile, and I keep cycling and nothing else changes, right?
Okay.
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 But that's going to be horrible, because we'd have to just keep doing that forever manually.
Yeah.
And so, for example, one of the things I could do, see if you agree, I could take this wall, the bottom one, bottom of the bin, and I could say monitor force on the bottom bin.
Oh.
The force on the bottom wall is equal to all these different forces from the particles that are touching it. Right? That's where the force comes from. So if you could somehow monitor as the system is running this value, okay, and then we could go and say, oh, here's number of time steps, 0, and here's force. It starts out at 0, and it's going to somehow go up and up and up, and eventually it's not going to change. You agree?
Yep.
Got it? Okay. So that's another thing we could do. And we're going to do this. And in the world of PFC, we can do these things very easily. So we can basically use a special type of logic called history. History means create a time history of a certain thing. And so we're going to say create a time history of the total force acting on this wall. Okay?
Okay.
And then once we have that history, as we cycle it internally, it's storing that data. And we tell it sample every 10 steps or sample every 100 steps or something like that. Okay, so it's just building up internally a big history. Then we also have the ability in PFC to use what's called plotting logic. And so we can make a plot, an image on the screen of this history versus number of steps. Okay. So this is one of the things we're going to do. Okay. So then we could go and we could just say, I don't know, cycle 5,000, and we could watch this plot. And eventually we keep cycling this much and then this much and then you say, oh, look, it's not changing. That's good enough. Okay.
Okay.
That's the general idea. And we're going to continue. I'm not going to talk more right now. But the thing to take away at the moment is instead of doing this, there's an even more direct way to do it, which is done with something called a solve command. So instead of saying cycle 1,000 and look at something, and cycle 1,000 and look at something, we're going to have some kind of a magic ratio. So hold on just a second. To make this even more clear, instead of that, let's take another simple step. So you agree we could do this and watch it.
Yep.
Right? But we could also do this. Now, this number, this value, let's call this F star. What is that going to equal?
Equals to the gravity of all of the things.
So I think what you mean is it's got to equal the total weight of all the particles.
Yeah.
Where the total weight is the summation over all the particles of the weight of a single particle, which is going to be density, mass per unit volume, times volume of particle, times acceleration of gravity.
Yeah.
This is mass of a particle. This is acceleration of gravity. That's the weight of a single particle. And if we go through all the particles, sum that up, we're going to get this. And so that's what should happen. So F star, we could verify, is equal to that, right? Okay.
Well,
then what we could say, are you with me? Okay, then we could say,
I'm with you, but I have a small question that will the maybe impact force will make some,
So I think what you're saying is if this is the wall, and let's say we just had one particle, it's going to come and it's going to bounce, and eventually it's going to not go anymore. So when it's all done, this force on the wall is going to be the weight of the particle. But if we plotted force on the wall, say that's equilibrium point, it's going to overshoot.
Yeah.
And this is called a dynamic effect, an impact force. And this will come in PFC because PFC is the true dynamic response of a real system. And so, yes, and so we'll see all this. We will be able to watch this. This is exactly what will happen, but we don't, basically it's going to bounce around for a while and then it's going to stop moving. And that's the state that we want to reach in this system. Okay.
Yeah.
And we can talk more about this whole impact business a little later. That's a good point.
Okay.
Okay. But we're just looking at the final, and it doesn't change anymore, right? So we could take, if we were sitting here, this is the current, this is what we call WP, weight of all the particles. And this is our value we're trying to get to. And so, sorry, this is not weight of particles. This is weight of particles. And this this would be, what am I going to call it? Force on the bottom, force on that wall. Okay. Right?
Okay.
And so we could take the ratio of this divided by this, going to 1, but eventually that ratio will equal 1 when we're at equilibrium.
Okay.
Agree?
Yeah.
So we could create a ratio, I'll call it epsilon, of, and actually we were calling it force on the wall, on the wall over weight of all the particles, epsilon.
Okay.
And we could say that when that thing gets close to 1, when this ratio gets close to 1, then we could say this is epsilon limit.
Okay.
So when this ratio gets to reach that value, we could say we're good enough. We're done. We don't have to cycle anymore. Okay. So this could be some criteria. We could sit there and say cycle until this value, which we would just keep measuring as the simulation is proceeding, we keep measuring this. And when this ratio reaches a certain limiting value, stop, you're done. You got enough. Okay, and we're going to do that. We can do that with PFC. But there's another ratio that's more general than that. Everything we talked about here, well, it has to be a box and filled with particles. But what if you have a general case? Totally general case. You got particles doing whatever they want to do. Okay. And you want to figure out, are you at static equilibrium? So think of it this way. Here's a particle. Here's another one. This guy's surrounded by particles. This is the guy we care about. This guy, draw him over here. 1, 2, 3, 4, 5. This guy has 5 forces acting on him.
Okay.
With me?
Yep.
F1, F2, you get it, right? So we could take the total force on him, I'll call it the unbalanced force, equals sum of Fi. You got that? Okay.
Yeah.
And remember, if you take the sum of the unbalanced forces, that's the total force. That has to equal mass times acceleration. Right? So we want the acceleration to be 0 when we're at static equilibrium. So we want this to be 0 when we're at static equilibrium.
Okay.
Because all the forces are summing to 0. Okay?
Yeah.
And so we could say, go to every single particle and check what its unbalanced force is, and don't stop until all of them are exactly 0. Okay. But unfortunately, because we are doing this on a computer works with finite mathematical precision. It doesn't, it's never going to equal 0. The sum of these things is going to end up coming to be some very, very small number. Okay.
Okay.
So what we always need to do is not look at absolute values. We need to look at ratios. And so you could say, look at the ratio of the unbalanced force. Let's say the absolute value of that, because we want this to always be we don't want to worry about plus and minus.
Okay.
And now you need some, let's call it F prime, some representative value for a typical system. Okay. And we can get that. We can base we could say, well, the representative value might be the sum of the absolute values of all these things or something. And so we could say when this equals some limiting value, then we're at static equilibrium. We stop cycling. Okay.
Okay.
And so this thing we're going to talk about, we call it the average ratio. So we're going to call this thing ARAT, average ratio. And we're going to have the ability to say, we're going to continue until this thing is less than or equal to this limiting value.
Okay.
So you're going to keep cycling until this thing reaches this small value. And the smaller we make this, the closer we're going to be to full static equilibrium. Okay?
Okay.
And we do this with a single PFC command called solve. And so we're going to say solve ratio average, and then we might say 1 times 10 to the minus 4.
Okay.
And so PFC then will continue to cycle until this value gets less than or equal to that.
Okay.
Okay. And we're going to play with this, and we're going to find out that for most systems, this thing, once you get 1 times 10 to the minus 4, you're at static equilibrium. Sometimes you might have to make this 10 to the minus 5. And of course, the smaller you make this, the more cycles it takes to reach that. And then we have to talk about things like, well, when is it close enough? Right? And it's going to be close enough. It's going to depend on your problem. But basically, if you look at, remember when you haven't seen much of this, but if you have particles, you can draw a line for the forces acting between them. Okay, we call chains. And the force chains are showing how the material is carrying load. Okay. And when it's forming a pile, these force chains are changing all the time. But eventually, when you get to static equilibrium, these force chains don't change anymore.
Okay.
And so that's kind of the point where, as long as we solve, force chains aren't changing anymore. For the most of the kind of things we're doing, that's fine. It's close enough. Like if we were doing an odometer test where we put on a platen and give it a motion downward of velocity, we could say, oh, well, as long as this is pretty much the force chains aren't changing anymore, if we run the test, we get a force versus delta curve. We talked about this, remember, right?
Yeah.
And you could say, oh, let's do a solve to this point and run the test and get a curve. Let's do a solve to a even more stringent and run the test and get a curve. Now, if you get the same curve, that means that's good. You didn't have to do the smaller one, right?
Okay. Yeah.
So that's why it's problem dependent, right? How close you need to be depends upon what is the thing that you're doing with the model. What are you getting out of it?
Okay.
So that's part of the big picture. We're going to eventually end up taking, just a second, remember we had this system that we're going to build right here, this system, and it's going to form a pile. And then we're going to learn how to say, oh, let's now put in a wall and give it a velocity. And let's monitor, this time the force on this wall, and let's monitor delta, and let's actually monitor it with the history mechanism. So we're going to do an odometer test. That's exactly an odometer test, right?
Okay, yes.
Right? So, and we're going to learn a whole bunch of stuff along the way of doing this problem, okay?
Okay.
And then the final big picture, so we're going to eventually create an odometer test.
Okay.
And by the way, we're going to do it so that we can create things with 3 different types of particle shapes. In PFC, there's a ball, which is a sphere or disk. There's overlapping balls, which we call a clump. So that's a different shape. Or there's rigid block, which is a polyhedra, right?
Okay.
We could then, we're going to do this, we can change particle shape very easily. And then
Yeah.
we'll be able to say, oh, let's do another. If we just have balls, maybe it looks like this. If we have clumps, maybe it's stiffer. I don't know. But we can look at the effective shape, for example. Right?
Okay.
Okay.
Yeah.
This is the kind of stuff people do. And then, and this actually, we're going to get to all this, and I'm working with an IEP student at University of Utah who is doing this. Her name is
Sorry, I think I'm lost. I can't hear anything.
Oh, Dave is lost for us. Hey Dave.
Am I still there?
Hey Dave.
still here?
We can. Okay.
Still here?
But we lost you.
Yeah. So did you get the thing about IAT, that I'm developing an environment to do
I
no
got
down?
lost when you talk about Anya.
IAT, yeah, AYAT.
Yeah.
So for her PhD, she's studying the behavior of hydraulic fracturing proppant.
Okay.
Who knows what that is?
Well, hydraulic fracturing proppant. Well, is it about the oil on the ground?
Correct. And so oil is usually in sandstone, because sandstone is porous, and when the oil forms, it can get trapped in the sandstone.
Yeah.
Usually deep underground, if that's the surface, there's going to be a layer of sandstone.
Yeah.
And the oil is going to be here because it forms, and if it didn't get trapped, it would not be there. And so this might be, I don't know, maybe this is limestone on both sides. And so that's where the oil is, okay? Do this quick thing. So here's sandstone. It's porous, it's filled with oil. Good.
Yeah.
Here's the surface. We want to get it. So the simplest thing is to drill a hole. Remember the rock cutting?
Yeah.
Drill a hole. Here's the surface. And because it's so first of all, when they drill the hole, what they usually have to do, because it might collapse because of the stresses, is they put a steel pipe.
Okay.
Steel pipe as they're going. Okay.
Okay.
And now they've drilled the hole through this whole formation, and it's got a steel pipe. So therefore, the fluid cannot. We want the fluid to do this, right? But it can't. So what they do is they drop down a special machine and they shoot a bullet through the hole, through the side of the steel, and make a perforation. Are you with me? So now they shoot holes in the steel. So now what happens, because there is a pressure here in this, it's if you're lucky, it's sufficient, and the oil just naturally pushes its way up. Okay. That's the simplest case. And if you do this, think of this as the region. There's going to be some region where the pressure gets less and less, and eventually you can't get any more oil out.
Yeah.
And so I think, and I'm not sure of the numbers exactly, but you probably only get maybe 20% of the oil out if you do this approach. Okay. And partly this is, and the main reason is because it's really hard for oil to flow through the sandstone.
Yeah.
It doesn't have enough pore space. So you only get the stuff local, and then you kind of dry it out, if you will. So what they do, they call it hydraulic fracturing. They go and they pump special fluid. Just think of it as special water for now. On the surface, they pump it in, and what does it do? It goes, so here's my sandstone layer. Here's my special fluid coming in. Here's my holes. Okay. Now this fluid goes out, and if you're lucky, it starts making a fracture.
Yeah.
And this fracture has got fluid pressure on it.
Yeah.
And if
of
that
course.
pressure is high enough, this fracture grows longer.
Yeah.
And it keeps growing longer till it relates to how much pressure you have and the strength of the rock and everything, right? Now,
Yeah.
you now have much easier pathway for fluid to go in here to go out.
Yeah.
Okay?
Yeah.
That makes sense?
Okay. Yeah. Yeah. Yeah.
That's the idea of hydraulic fracturing. However,
Okay.
there's very high stresses down here, and they're all compressive. Okay?
Yeah.
So
yeah.
when I have the fluid pumping in, I have a stable opening, a perforation, a fracture, and it has an opening delta, which is greater than 0, and therefore fluid can flow. But when I turn off the pumping, this pressure is 0 now, and this thing closes back down. Delta equals 0, which means after I'm done pumping, I haven't done anything helpful because I've made a fracture, but I have not increased the permeability because the fracture closed. Okay.
Yeah. Okay.
So someone had the idea and said, we want to somehow, so here's when it's pressurized, it's actually open. What if we put some pellets, like little BBs, like we put in a gun, little pellets. And if we could make those go and flow in here along with the fluid, and these are very strong. So now when I stop the fluid, you still have propped open, so they call this proppant.
Okay.
So that there's a delta that's greater than 0 when you're done.
Okay.
So now it's easier for the material to the oil to flow. That make sense?
Yeah. 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 Yeah.
Okay. So this is proppant, and they have typically they go and use sand.
Okay.
Because you need a lot of this when you do a hydraulic fracture. This is very large scale. These can be 100 meters or more.
Okay.
And so they need something. So they often would use sand originally. And the sand grains, because also the sand grain can flow in the fluid. Remember, it starts on the surface. It has to get carried by the fluid into these fractures. Okay. So, and then it has to be strong enough. Here's the next question. When this stuff gets pressed, you don't want the proppant to break apart, because if it does, it's just going to pack itself in and it's not going to be useful, right?
Yeah. Yeah.
Okay. So you want to have a strong enough proppant to not break. And so there are people who have made now ceramic proppant. Okay. So this is a man-made thing. It's a ceramic. Okay. You can make this in the laboratory. And you can make it so it has a density that's a lot less than the density of sand. So it doesn't have as much weight, so it flows better when it gets carried down. Okay. And so you can engineer this material. Okay. And again, one of the properties is you want to have strength. I'll call it sigma prime. That's the strength. It has to be strong enough so that it doesn't break. And so why is it going to break? It's a function of the in situ stress, but it's also a function of the temperature. You can have, nowadays, they are extracting oil from areas that are very hostile. All the places where you could easily get oil have already been exploited. So now you're going deeper. If you go deeper, the stress is higher. And if you go deeper, the temperature is higher.
Yeah.
And so both the stress and the temperature affect the strength.
Okay.
So she is looking at, she's doing laboratory tests to measure the effect of stress loading, the stress loading and the temperature on the strength of proppant.
Okay.
And so, you know, one way you could do that is do an odometer test. Fill up a cylinder, push on it. Measure force, measure displacement. If nothing breaks, it does this.
Yeah.
If it breaks though, it starts to break and then it gets less stiff.
Yeah.
Okay, that makes sense?
Okay. Yeah.
Does that make sense? This is a measure of breakage because it's deviating from linear stuff. Okay.
Yeah.
So she's measuring this in the lab for different conditions, and she's also going to do PFC 3D models of the same thing, of the breakage of the proppant. So does that make sense? That's a real world problem, a real world research problem that's currently being addressed with both lab tests and PFC.
Okay, I got it.
Got it. And because she's my IEP student and I'm trying to teach her how to do this, I use this as an opportunity to create a well-defined, I call this an environment, an OT package. It's a package of scripts, fish functions that allow you to very easily perform odometer tests, OT.
Okay.
And with that package, I have an odometer test memo, which is a detailed technical memo that describes everything of this package and about how to run PFC and the important aspects of PFC you need to understand to do this. Okay. So we're going to end up, that's why we're using this odometer test as an overall example to introduce everything about PFC. Okay. Because we're going to eventually get to the point then where I can say, oh, here, I'm going to give you this package and you're going to play with it and you're going to read about it in here and you're going to get a firm grasp of how PFC behaves. Okay. And notice, this is so cool. Everything we talk about is very simple. It's granular. There's no bonding. This is not bonded particle modeling. That's the next step. Okay. Isn't this fun? Okay. I got a good plan here. And you can see how I've never done this before. You are the first. I am developing this as we go. And I think this is going to be a good way to teach people PFC. Okay.
So I'm going to try that.
Correct. Now, one more step here. This is even potentially more exciting. I've been working with another PhD student named Marley Reed. And she has looked at bio-cemented sand. Do you know what this is?
Actually, I don't know much about it.
Okay, so here's what it is. This is another relatively recent idea people have had. Let's say you're building a big building, like say in a area where there's a lot of other in a downtown. So you have to basically make a big giant pit. Right? And support that pit.
Yeah.
And then you have to have foundations, perhaps. And here is you build your big building on these foundations, right? Now, the strength of how you design this has to do with I'll call it sigma prime again, the strength of the soil. If the soil is really, really strong, this is easy. And you just build your building. Okay.
Wait, maybe I know that. Are we use some biological thing to make the solid stronger? Is about that?
Yes, you're so smart. Yes, exactly.
Okay, yeah, because we have did some similar experiment in the lab when I was undergraduate.
Tell me more. Wait, really?
Yeah. Well, it's about I should search it's about a carbon mine. Is that?
Carbon mine? A mine? To get material? A mine?
I don't know the English word, but it's
Okay.
maybe it's yeah. So we use some biological thing
Okay.
to add it to the solid and wait for like 7 days,
Yes.
21 days, 48 days. Yes, and then
Yes.
we test the shear strength of it and find out it can make the solid stronger, and it affects by the days, by the numbers of the biological things that we added. So we
Yes.
found, yeah.
So were you assisting a professor or a graduate student doing this?
Actually, not I and another student, we two applied a indoor case by a project of our school, and so it can provide us the lab and some money to do it.
So it was part of a course assignment?
Actually, it's not a course. It's like sorry, I need to search it.
It's okay.
Yes. Oh, okay. Sorry. Please just wait for a second.
We have plenty of time. Don't worry.
Okay. Well, the internet doesn't work. So
Okay.
I can describe it as simply, it's like a research encourage project to the undergraduate students.
Yeah, okay. So because you just finished your undergraduate degree, correct?
Yeah.
Got it. And while you were doing your undergraduate degree, you were also doing undergraduate research.
Yeah.
Okay, and that makes sense because you're a smart person and you like this stuff, and that's why you've been accepted to go do a PhD with Frank. And got it, right? Is that right?
Yeah.
Okay.
Yeah.
And that's why it's really fun to give you this course, because you're really smart and it's fun to work with you.
Thank you.
Got it. So, okay, so you know a little bit about this bio-cemented process.
Yeah.
And so, again, it's exactly what, if we go back to my picture here, the idea is you can put in some holes and you can pump in this special bacteria agent. And if you pump it in, it slowly percolates out. And then if you wait long enough, it cements together the grains, making them stronger, we hope. Correct?
Yeah. That's what
Exactly
we do, but
right.
we do a small thing in indoor lab.
In the lab, exactly.
Yeah.
And so, so as my understanding is, at this time in the world, there are many researchers studying this process. And that's an example of what you did. And so Marley Reed, who just finished successfully her PhD, was studying this topic, okay? And what she was doing was in the laboratory making small samples, and this was, I don't know, 50 millimeters maybe. Okay. And no, it's bigger. Wait a minute. It was, they were bigger. They were, you could hold them in your, I don't know, what's the 200, maybe 250 millimeter diameter. Okay. They were not giant, but they were not tiny. Okay. They're bigger. They're about the size of a coffee cup. There we go.
Okay.
I'm always drinking coffee. Okay. She took these things and she said, okay, she had a mold, like a big steel frame with a big steel thing that had a hole, that had an opening in it.
Mm-hmm.
and she took sand.
Mm-hmm.
She had what's called a funnel,
Mm-hmm.
and she started with dry sand, quartz sand, and she let it fall, and it formed a
Mm-hmm.
pile, just like we're doing. Does this sound familiar? She
Okay.
let it form a pile, and after it was stable, she then took a steel platen
Mm-hmm.
and she put a certain amount of weight on top and like pressed it down. And that was the initial state of the dry system.
Okay.
Okay.
Yep.
And
Yep.
then she went and she pumped in, she made it flow through the system, this magic stuff,
Yep.
which I call an elixir.
Okay. Elixir.
Elixir is a really weird, fun American word. It's sort of like a magic potion. Like if you were
Okay.
Harry Potter and you were a
Mm-hmm.
wizard and you mixed up some special stuff and you drink it
Mm-hmm.
and it does something, that would be an elixir. So it's like
Okay.
magic liquid. Okay. That's
Okay.
what I call this. So she pumps
Okay.
this through, but this is that bacterial stuff.
Mm-hmm.
And then she, pumps it through for, I don't know, 24 hours, and then she lets it
Mm-hmm.
sit and she waits 7 days, just like you
Mm-hmm.
said, or she waits 14 days. Eventually, it doesn't change
Yep.
anymore. And
Yep.
then she took this and
Mm-hmm.
she took it out of this and she went to a
Yep.
different laboratory, and now she has
Mm-hmm.
a cylinder, and
Mm-hmm.
now she does a uniaxial compressive strength test.
Okay.
Do you know what that is?
Yeah. I know.
Okay,
It's
this is a
just to
typical,
compress it and
exactly. And so
yeah.
you plot the axial, you take the force
Mm-hmm.
on the platen divided by the area, you call that the axial stress.
Mm-hmm.
You measure delta. If this is L, you compute the
Mm-hmm.
axial strain, which is delta over L.
Okay.
Are you with me?
Yeah.
Okay, you plot this, it goes like this, and then it goes up, and then eventually it breaks. And you call
Yeah.
this the UCS. It's a very, very common rock mechanics, very, very simple test to get a very crude measurement of strength. Okay.
Yeah. Mm-hmm.
And this then so what she was looking at, remember I said she
Mm-hmm.
made material. She had
Mm-hmm.
different grain size distribution. Do you know what that is? If we
Different
do,
grain size distribution.
so
Okay.
this is percent passing,
Oh, yeah.
100, 0, and
Mm-hmm.
this is grain size.
Mm-hmm. Okay.
So her grain size might have gone from, I don't know, 0.1 millimeter up to like
Mm-hmm.
3 millimeter.
Mm-hmm.
And then this curve, right?
Mm-hmm.
It ends up going something like this, right? Which has to
Okay.
do with percent passing. Which you know about these tests, you take the
Yeah. I know.
material, you have sieves, like little screens,
Yeah.
and you shake it and you measure the amount on each screen.
Yeah.
And you figure out what you make this plot. And
Yeah.
the
I know this.
characteristics of this curve, this is called grain size distribution.
Okay.
This is the typical way that people, I call it a
Describe.
GSD. It's a typical way
Okay.
of trying to quantify
Mm-hmm.
the shape, the effect of, not shape, the effect of size on a granular
Okay.
material. It's a way of quantifying size, right?
Okay, yeah.
Okay, because if you have a granular material where everybody's the same size, it has a
Mm-hmm.
certain behavior. But then if you put a lot of small guys in here, it fills the gaps.
Mm-hmm.
And now if you add a bunch of small guys and big guys, this guy is stronger because it's filling the gaps. This is just a basic example of grain size distribution has a big impact on the overall response in terms of strength and deformability. And so she did 5 different typical grain size distributions and then looked at how did that affect the UCS.
Okay.
By building those materials. Make sense?
Okay. Yeah.
Makes sense? Okay. And she also looked at, her specimens after they broke in certain way, kind of split into a few pieces. Or they would do things like this whole chunk would fall off, and then this would be a big chunk here that would fall off. And actually, when she did the test, these things would fall off and a whole bunch of sand would pour out. And because sand is pouring out, it means that internally it's not perfectly connected. It's not cemented uniformly. This is like something learned from doing this work. Now, going back to the world of PFC, she used a particular PFC contact model, which we'll talk about. This is a bonded particle thing called a parallel bond. And what a parallel bond does, imagine two grains, they're touching. It's granular material. They can only take compressive force. But now imagine that you put cement here in this region. Does that make sense? Okay. And this system now, after you add the cement, is going to be stiffer than the system but without the cement.
Yeah, of course.
Okay. So this is how she modeled. Remember, she started with the system of a pile. And then she applied a weight, and she could measure the stiffness. And then she puts the biocement in there, which is doing this. This is really what it's doing. And then she measures a bigger stiffness because of the cement, right? So she used the parallel bond model to investigate these effects because she did exactly this. She poured it in, she simulated this, she put the cementation in by adding parallel bonds, and then she did UCS test. Okay. So what we're going to do is once we have our odometer test set up, right? So what does the odometer test let us do? It lets us drop in particles, fill itself up, put in a wall, and measure force displacement, right? Well, it's not very hard. We're going to take this, and now we're going to go and add parallel bonds. And then we're going to remove these sidewalls so that now we have a UCS test.
Okay.
And so now when we plot force displacement, this is a UCS test and it breaks.
Okay.
That makes sense?
Yeah.
Okay, that's where we're going. And also, because I worked with her, I created a package that she used as a starting point, and I call this the cemented sand package. And again, I wrote a memo that describes it all, so that is a basis for her to start doing her work. Okay. So we're going to do all of this as well, and then you'll get to look at that memo and see what you think. Okay. I mean, I did part of all this and made these memos and packages because I was hoping that I could incorporate this into the PFC course. And so that's why that's what I'm doing now. And you're the first person, and we're going to see how this goes. Okay. So just think, once we get to this point, you will have an understanding of working with PFC and actually going from a granular system to a bonded system. And so this should put you in a good place to then move forward with your own work. Okay. And so, and all of this is going to take a while. This is where, this is the roadmap that I wanted to go through of the big picture of where we're heading in these sets of lectures. Okay.
I totally get that.
Okay. And what I would like to do is continue having these weekly, 3-hour sessions, which will just slowly build on each other. Okay. Here's a practical question. Are you going to be available to do such things for the coming at least like 4 or 5 weeks?
Yes, of course, because I'm having the summer holiday, so I have a lot of time.
Oh, good. Okay, this is working out perfectly then. Okay, I'm also available the whole time. I don't go anywhere till mid-September. So this is good. When will you go to Tongji? When will you go?
Oh, well, I don't know yet, but I guess it's like the end of August or the start of September.
Yeah, okay, because that must be
Mhm.
when classes and things start. Okay.
Yeah,
Yeah, this all works good. Okay. So that's the plan. That's where we're going. I think it's going to make it's going to work good. We're going to do all this step by step so that you understand as we go. And
Okay.
so we're halfway through this lecture. Let's take a break. And then we'll
Okay.
come back and we'll jump into the PFC physics. Okay.
Okay.
So let's
Okay.
see. The time that I have here is 9:38. It's
Mhm.
probably 10:38. So let's go until 9:50.
Okay.
So we'll have a
Okay.
break until 9:50. I will see you back here. Okay.
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 Okay. I'll just leave this all running, but I'm gonna disappear. Okay.
Okay. See you later.
Okay. Already. Yeah. 9:50. Sounds good.
Okay. 休息一下。哎呦。
Hey there. Can you hear me? No, you can't. Okay. No. Hey, Dave. Can you hear me? 我不知道他听没听得到。
Okay. You guys hear me?
Oh, hi. Yeah.
Okay, excellent. It's so awesome. You know, you guys can talk in Chinese all about me, man, and I have no idea what you're saying. I'm sure it's all good.
Now we're not talking. This time we're all eating.
Yeah, we're eating.
Oh, you're eating. Oh, food.
Yeah.
Oh, yeah. Okay, see, I have to keep you entertained as a showman because it's late at night at your house, right? What is it? 10? Is it almost 11 p.m.?
Yeah.
2300. In China, do you use 11 p.m. or do you use 2300?
We use 11 p.m. maybe.
Oh, you do use p.m.
11 p.m.
Yeah.
So it must just be Europe that uses 2300. That's interesting.
Maybe.
Okay. I mean, I'm so lucky in my job. I get to travel all over the world, and you know there are some places that use that other system. In the United States, the only people that use 2300 are the military guys. They use that for some strange reason. Okay,
Wow.
share my screen. here we go. Tell me when you can see it. This is an important picture.
Oh yeah, we can see it.
Look, okay, I'm doing this from home. It's perfect weather right now, morning time, 65 Fahrenheit. I don't know what that is Celsius. It's beautiful, sunny. This is my backyard. This is my garden. Notice here, this is, okay, Shihang, see if you can translate. Cucumber, right here, cucumber. Do you know what that is? Pickles?
黄瓜，黄瓜。
Cucumber. Oh, cucumber. Okay.
Okay, now here's a harder one,
Cucumber.
Shihang. 1, 2, 3. These are called eggplant. Eggplant.
茄子。
Eggplant. Oh, okay.
Okay?
Okay.
These here are tomato,
Okay.
and this is raspberry fruit.
Raspberry.
Raspberry. Now,
Oh, okay.
one more picture, and this here is the deck I built. You'll see this later, maybe. Shihang, remember I sent you a picture of the deck.
Yeah, I
you
gave
need-
you a reply about that.
I know exactly. I said you need to, when you come to visit me, you need to come. We'll sit on the deck and we'll drink beer.
Yeah,
And
I will.
Yung King, you also you would need to come visit me. Perhaps in your research career, you'll get a chance to come to Minneapolis.
Okay.
You can always come visit me. And look at this. This is a honeysuckle. I like to have plants that grow up on things. And
Mhm.
so, 2 months ago, there was still nothing growing. So it grows so fast. And so if you zoom in on this, you can see, isn't that cool?
Yeah, what plant is it?
It's called honeysuckle. It starts from 0 at the ground. Every winter, it dies all, and it grows from the ground up.
Okay.
And you can see I make my little strings, and then I make my strings up here, and see it's going to start to fill this.
Yeah.
So we will take a picture of this garden every time we have a lecture. And so we can see how much bigger this is going to be in a week from now. Okay.
Okay.
Last
That would
thing
be
before the physics,
Mhm.
remember we talked about biocemented sand, right?
Mhm.
The
Yeah.
biocementing. Okay. So
Yeah.
this, as you may know, this is my latest research, this subspring network breakable Voronoi model, which may be possibly something you end up working with.
Mhm.
In this paper, I have a picture of biocemented sand. So I wanted to show you that. Just a second. I'm a picture guy. That's why I have all these figures in here. Right there. This is crazy. 50 microns. Look at this. These are simply 2 grains of sand. And that's the cementation that has formed. I am amazed at these microstructural pictures because when we think of grains of sand, we think of these nice, simple, smooth, couldn't be more simple than a grain of sand, right? But if you actually look at the surface of a grain of sand, it's crazy. It's like a rock mass. It looks like, to me, this looks like the surface of the moon.
Oh yeah.
And so, it's interesting. It's also, you may find this to be of interest. Often how research works is you're thinking of something in your head in the background, and then you're doing research. And so while I was doing this research, I had to come up with a way of breaking a grain. And so this is, now it's a bigger length scale, 0.35 millimeters. This is a rock, a granite, and this is a grain. And you can see the fracture. See how it's come from upper right? It's gone along the interface. It's split the grain. It went up and it went down. You see that?
Yeah. Yeah.
Right?
Yeah.
And so this, we call this a transgranular crack. It's going across the grain and breaking it. And so in order to I had to come up with a way of deciding the strength of a grain. And so I ended up coming up with a certain way to do this. And the way I came up with it is by thinking of the grain at this, because I was doing this work in the biocemented stands. And so I was thinking of this. So I was saying, look, this grain is very complicated. And so I ended up treating it, the grain itself, as if it was a rock mass. And I use a very common failure criteria that is used, for rock masses, which is here. We're not going to talk about this, but this is basically, if you are in the world of rock mechanics, this is the failure criteria that you use for rock. And I basically said, look, that grain is like a big hunk of rock, because it's not simple. This is like a big hunk of rock. So it's kind of interesting. I think this is how a lot of research works. It ends up being presented in a paper as if it's all logical and everyone just thought through the math and this was what you came up with. But in the real world, it almost never works that way. You're thinking of different things in the background, and then you put these things together in new ways. And then in the result, when you write the paper, you often don't talk about that. And so, but this is actually how it works, right? And so to be a good researcher, it's very helpful if you are a very curious person and if you have many interests in different areas, because it's by bringing those different things together that you get new ideas. So that's what I wanted to share with you. Okay. PFC physics. Here we go. Now we already went through some of this, so we're going to go to where we were before, and I've just lost control of my screen. Oh, here we go. Wait. Oh, it's because I'm done with this one. Just a second. PFC physics. Okay, let's get to, just because look at this. Can you hear that in the background?
We can't hear other sounds.
This is a rock cutting test. We talked about modeling rock cutting.
Okay.
That's a rock cutter. That's 10 millimeters across, and it's being pushed through a certain kind of sandstone.
Okay.
And when they do that, they plow these grooves. And when they do that, they measure force. And they change depth of cut, and they get different forces. And they change angle, they get different forces. And so this is what this is what we're modeling here in PFC. This is how they generate these curves. That's all I wanted to point out. Okay.
Okay.
That was based on what we did before. Now, where are we? We're here at the beginning. Okay. This is a review. This is the big picture. Everything about discrete elements is on this slide. Discrete elements, which we call particles, they're rigid. They don't change shape. The particles in PFC are balls, clumps, and rigid blocks. And they move around and they start to touch. And when they start to touch, we call it a contact. And at a contact, we have a force, equal and opposite. You can see the green is a force. At this contact, there's a force pushing up and there's a force pushing down, and they're equal and opposite. And so you can see this case, here's the three walls. This is just like our odometer test, right? We start with three particles. It's the simplest possible odometer test. And we push with the wall and we look at the forces, right? And we're going to be looking at the sum of these forces because that's the force acting on the bottom wall. And we're going to look at the motion of this, and that's going to be the delta divided by the length. That gives us strain. These forces divided by this area gives us stress. And then we're also going to look at this. This is the total force pushing on the top, right? So we have contacts. We embody the physics of Newton's law, and we do that by discretizing this differential equation. And if we do that, we call this distinct element method. And therefore, we call this a dynamic simulation. We're moving forward in time. And therefore, the time step is an important thing. And we'll talk more about this, but we went through this general idea. It's based on the mass and the stiffness. It's going to adjust itself.
Yeah.
And the other thing we haven't talked about is there has to be some kind of way of dissipating kinetic energy. If I take that cloud of particles we're going to do and let it fall into a box, it has to stop bouncing around.
Yeah.
And that's what damping is. It's a way of dissipating energy. Think of it like in real world, when a particle is dropped, like a tennis ball is dropped onto the surface, it doesn't bounce up to the same height.
Yeah.
It loses energy in the process of deforming itself and undeforming itself. It's actually a deep, complex question. What exactly is the physics going on? Why does that lose energy? And it has to do with very, very small molecular level behavior. When you squeeze a material and you unsqueeze it, you actually do some damage at the molecular level. That's part of the reason of what's going on with kinetic energy loss. And we don't do that usually. We just get the result is that we lose kinetic energy. So there's different ways in PFC that we're going to make that happen. Okay. Okay. We're going to talk about all these things. Now, here we go. Simple model. All my slides, I try to keep them very clean. Notice there's not any stupid logos on here and junk like that. The idea is that every single bit of pixel that's not white should be there for a reason. If there's not a reason to make it more clear to you, it should not be there. So all my slides always have a summary at the top, right? So here we go. The basic idea is it's a simple model. What do we mean by that? We mean that there's only two things in it. There's particles and contacts. That's what I mean. Okay. So let's look at what the particles are. Just like we said, three kinds: balls, clumps, rigid blocks. Look at these guys. They're crazy, weird things. There's particles and there's contacts. And here's the contacts, like we saw before. And so these particles, now watch, there's more coming. These particles interact, right? Unless there's a contact, that particle doesn't know anything about anything else. It only knows about the rest of the world because it's getting pushed at its contacts. Now, at the contact, what are we storing? You tell me.
At the contact, what do we storing?
Or what's happening? What's the contact doing to the particle?
Okay. Oh, well, so in the thought, there will be a space that covered by each other, and then well, in reality, it means that the first particle will how can I say that appearance, the force to another?
The force. Exactly.
Yeah.
Every contact has a force that pushes against one particle and an equal opposite force pushes against the other. Okay?
Yeah, pushes. Yeah.
It's a force.
I forgot this word.
And so each contact has a force that acts on the two contacting surfaces. Notice I'm saying surfaces, not particles, but a particle is made up of a surface. So if it's pushing a surface, it's pushing a particle. We'll see why that's needed in a moment. And here's the idea of a force, right? These two guys are pushing against each other. And notice they're not just in a normal direction force. That force is offset a little. So there's a normal component and there's a shear component there. Okay? But it's equal and opposite. Okay? There's also the possibility for there to be a moment acting on both of these guys. And this is showing that there's an equal and opposite moment, right? I'm drawing a moment as a
Okay.
little rotator, right? Like if you take the right-hand rule, if you put your right hand out and you grasp this axis and you rotate to the counterclockwise way with your
Yeah.
thumb pointing at you, this is positive. Okay, and if you look at this one, it's the opposite. You're rotating the
Okay.
other way, right? They're equal and
Okay.
opposite, so they're in equilibrium. Okay, and think about one of the first postulates that Isaac Newton came up with his 3 laws of motion is that every 2 bodies in contact, there's an equal and opposite force acting there. Okay.
Yeah.
This is all about equilibrium, but this is fundamentally is one of the first people, the first guy to point that out was Newton. Okay.
Okay.
So how could you possibly get a moment? What do you think?
How could I possibly get a moment?
Yeah, how could there be a moment there? If you push these guys together, you get a force. But how
Yeah.
could you get a moment? How is that going to happen?
I think I don't.
Shihong, go.
Oh,
What'd you say?
Oh, the moment. Okay, the moment is the force, but not the moment.
Oh, no, I mean a moment. I mean a bending moment. Here, can you see my screen? Oh,
yeah,
no,
yeah,
you
I
can't.
got that. The bending moment.
Do you see I'm trying to share my screen on, do you see where I can write?
Yeah, we can see that.
You can see this.
Yeah,
Oops,
yeah, yeah.
sorry. My pencil keeps turning itself off. Okay, here we go. Think of a particle. Whoops, my pencil, it turned itself off. Just a second. Come on. Oh, my pencil's running out of charge. Oh, I think I've lost my charge. Just a second. This means I have to, this is all new technology to me to be using a pencil to lecture. Okay, my pencil is out of charge, so we can't do that. So just a second. Let me stop sharing. Stop sharing. How do I do it? Stop presenting. Are you back with me here? Can you see my
Yeah.
Can you see my PowerPoint?
Oh, no.
No. Okay, just a second. Share. That's not right. Cancel. Just a minute. Share. Boom. Now can you see my PowerPoint?
Yeah.
Okay, here's the moment. Let's talk about the moment. I'm gonna have to draw in PowerPoint. So watch this. Here's a particle. Yeah, what the heck? It doesn't have to be, this has nothing to do with the shape. So let's make it even more exciting. There we go, 2 particles. They begin to touch. Okay, you with me?
Yeah.
Okay, watch this. Now, this guy. Just a second. Let's do it this way. I want to make an X so that I'm going to show that it's not moving. So here we go. Big. Okay. Okay, this guy cannot move. This guy's fixed. With me? Okay.
Yeah.
Let's get rid of the fill so we can see better. Let's get rid of the fill. Okay, so first of all, you're going to find out in PFC, at every contact, there's only 2 particles. There's not 3. Okay, and if you think about, this is like a circle. This is like a radius. If you think of spheres, if you have spheres, no matter how small they are or big they are, they can only touch there's only pairs of 2 that can touch.
Yeah.
Okay, and that's because we don't, for example, have this. If you had these shapes, like this, now, if these were the shapes, now it gets complicated because you could have like 3 of them touching at a contact, right? But you can say, well, hold on. You have rigid block. That rigid block could have that shape because it's just a polygon. So I say, let's talk a little more. Rigid block. Let's zoom in here. Let's ungroup, arrange, ungroup. Now, let's zoom in here, just like zooming into that sand grain. Okay, so that picture in your head, you were thinking it was this, that it was a perfect angle here, okay? The rigid block is not that. The rigid block is actually this.
Okay.
A rigid block is a rounded corner.
Okay.
That means that you've got, if you had rounded corners here and you had 3 of them, the surfaces are actually just either straight lines or parts of a circle. And you could only have 2 of them touching. Look at this. This is a close-up of the rigid blocks. Do you see the rounding?
Yeah.
You see the rounding? Okay.
Yeah.
So rigid blocks are actually, they're not actually polyhedra, which are just flat surfaces that are connected. They are, they're called spheral polyhedra, which means it's a mathematical thing. It means take a polyhedra and take a small circle and move the center of the circle around the boundary of the polyhedra. And in the process, you will create a whole new shape, and that shape will have rounded corners.
Okay.
And that's what the thing is, right? If you took this and you went like this, right? If this guy was here, that's a polyhedra, but we don't do that. We take this and we make a new surface that looks like that. And then we go around and notice if the center goes there and then the center goes there, the result is we get a circle on these corners disappear. Okay. So that's what we have in PFC. That's why every contact is only between 2 particles. Okay. Now, remember, we're trying to get to the moment idea. So this guy's fixed. This guy is going to have a motion, delta, a translation. So let's make it go the other direction. Like this. And it's the centroid. So the centroid is going to move. Let's make it move straight horizontal here. Okay. So let's make that red, make it a little bigger. So the center, here's this particle. Make that particle red. Okay. And this is a motion, a velocity we apply. And so for whatever reason, that particle has that velocity moving in that direction currently. Okay. Okay. Now we take a time step. So this particle moves that way. You with me?
Yeah.
Okay. So let's make this one freaking dashed.
Okay.
So that's at time t. This is where it is at time t plus delta t, right?
Yeah.
Got it? Okay. And this one is not allowed to move. So at the new time step, it's still there. Okay. So what's happened here now? At this contact, a little piece of this surface has moved this way. Okay. Which means we can decompose that into a certain amount of motion normal. See, we're normal to that surface. There's a certain amount of motion this way plus a certain amount of motion in the shear to that surface. This one is supposed to be in the parallel to the surface. We'll call that a shear direction.
Okay.
And this one is normal to the surface. We call that a normal direction.
Okay.
With me?
Yeah.
Are you with me? Okay.
Yeah.
So check this out. This is delta V, but it can be decomposed into a local coordinate system. And that local coordinate system is set up so that there's a tangent to the surfaces and there's a normal direction to the surfaces, right?
Okay.
So, okay. So we could, for example, call this then F sub n.
Mm-hmm.
That's F sub n. That's F sub s.
Okay.
Okay. And so
Yeah.
there's going to be a corresponding force. There's going to be a normal force that builds up, and there's going to be a shear force that builds up. And if you sum
Yeah.
those up, you get a single force, equal and opposite. And that's
Mm-hmm.
what I've been drawing with these things. Single
Yeah.
force. Notice this is not directed from center to center. This has been rotated a little. See that?
Okay.
This is rotated because of what I said. This guy pushed straight down. When he pushes straight down, some of it is in a shear direction, some of it is in a normal direction. So there's a combination of normal and shear force acting here. That's why it's not a straight line from center to center.
Okay.
Okay.
Okay. I got that.
Okay. I think you,
Mm-hmm.
okay. Now, this is just the thing we applied was a translational velocity.
Mm-hmm.
Okay. Boom, translational velocity. Now, let's apply a rotation. So let's go down here, do the same thing, but this time, so first of all, if I have a rigid body and it moves in space, it can both translate and rotate. Do you agree?
Yeah, of course.
This is fundamental rigid body mechanics. Again, Newton was the first guy to quantify all this.
Yeah.
So the general system is not just translation, it's also rotation. And so PFC is doing this. In two dimensions, the translation just has two components, X and Y. And the rotation is just one component around, it's like that, the axis is in the Z direction. Think of the right hand rule, spinning your hand, okay? Are you with me? Okay.
Yeah. Yep.
In 3D, the translation has three components, and the rotation is a general axis that can be oriented any way in 3D space. Okay.
Yeah.
Okay. So going back to the 2D case, now if we want to talk about rotation, let's put a center on this guy. That was the original center, and now the center's moved over here.
Okay.
Let's first do this. Get this out of here. Hasn't moved yet. So what do we apply? We don't apply a translation. We apply a rotation.
Okay.
So that means let's do this.
Yeah.
Are you with me?
Yep.
Right hand rule. So instead of being V velocity, this would be, let's call it theta.
Okay.
Okay, you know what theta is?
Yeah.
This is theta. Let's just make sure. This is the Greek symbol for rotation typically, right? This sucker here.
Yeah.
Theta. We apply because we're not applying forces, we're applying motion, right? When we compute things, we compute motion. There's an increment of motion which makes things move. And when they move, they start to overlap and forces and moments develop. Okay, so now this thing, this guy doesn't move to the right. This guy does this.
Okay.
Right? It's still sitting here.
Yeah.
And let's pretend for this to make sense, this guy needs to have an overlap to begin with.
Okay.
And now this guy has done this. Okay. And so now let's try to draw this in a way it's easier to see because I'm not a good enough drawing person. So let's just do a similar simple case here. Let's assume they were circles. And let's assume then that, so this guy is fixed. Whoa, that's too big. This guy can't move.
Mhm.
And this guy rotates. Just a second. Let's see if I can steal that one.
Mhm.
Where is my rotate, man? That didn't copy that. Delete. Thought I copied it. Well, yeah, see, if I had a pencil, it would be easier to do. That I want to copy that.
Okay.
I'm trying to draw this. There, this guy. Here,
Okay.
rotate.
Mhm.
Ah, got it. Yes, good. Okay. Now,
Okay.
think of this, okay? This guy rotates. Now, pretend that there was an interface here of a certain finite width. This guy is somehow connected to that particle. So when I rotate this particle, this whole system rotates. So this thing does this.
Yeah.
You with me? Are you with me?
Yeah.
Okay.
Yeah.
And pretend that there's also a corresponding surface on this side that's
Okay.
glued to the other particle.
Mhm.
And so let's draw this and make this the gold. This guy's rich because he's built out of gold. Okay, let's see. Boom. And this guy's connected with that. Let's see if we can make this guy gold too. Oh, that's so cool. Okay. Okay, arrange group. And this guy doesn't move. So this guy, when I redraw it, just looks like this.
Yeah.
Okay. Now,
Okay.
when I rotate this, notice here, let's make this red so we can see it. Those two surfaces are overlapping. So this is going to be a compressive force.
Yeah.
Do you see how that would be compressive?
Yeah.
On the outside, it's high compression, less, zero here. And there could be tension here. Okay, potentially.
Okay.
So then there could be on this other side.
Why there should be tension?
Because, just a second. Just a second. Let me get this drawn here. And let's get this guy, move it over. Okay. Pretend that it started like this and they were glued together. Okay.
Okay.
This is a bending problem. So I now go and I rotate the top. So those two surfaces start overlapping. But these two surfaces pull apart.
Okay, okay.
But if they're glued together,
at
it goes in
the
tension.
beginning. Yeah,
Okay.
of course.
And
Okay.
there's the opening is biggest here, gets less, and then it reverses. So there's actually a distribution of compression on this side, tension on this side.
Yeah.
Okay. Now, if I integrate tension and compression, I get a moment. This is like beam bending. Does this make sense?
Yeah.
The way that this motion gets resisted by producing a moment that acts equal and opposite to resist this motion.
Yeah.
Okay.
Yeah.
And this moment is only going to happen if I have some kind of glue here. If I have these surfaces connect, if they're not connected, when I rotate this side goes into compression, but nothing happens here. And so the result is a moment doesn't form and this thing just moves. And, you know, it just makes, I think you get the idea. So in order for a moment to develop, notice that there has to be a finite length of some kind of connection between these things.
Yeah.
If there's no finite length, there's no moment that can build up.
Yeah.
When you apply rotation to two surfaces, there has to be some distance, which you think of as like a moment arm, where there's compression and
Okay.
tension.
Yeah.
Because the only way to resist a moment is to have compression and tension, because that's what builds up the
Okay.
moment. Okay, make sense?
Yeah. Yeah, of course.
Okay, so the general case is there's tension and compression. It's going to turn out that for the granular systems, where there's no bonding, you're never going to get moment. But as
Yeah.
soon as you put in cement here, now it can resist moment.
Okay. Yeah. Okay.
And so that's why in the general case, there can be in PFC, because it can handle all of this. It can handle, there can be a force and there can also be a moment.
Okay.
So, excuse me. So this is what's going on. Motion occurs, and at these contacts, forces and possibly moments develop. And those forces and moments are acting on the two surfaces. Okay.
Okay.
Okay, so that's the physics. Now, again, in 3D, the simple case, these are spheres. We call these balls. And in 2D, we still call them balls, but they're actually discs. And they're discs of unit thickness. That's what I'm trying to show here, okay?
Okay.
The 2D model is not spheres. The 2D model is discs of unit thickness. And here is a physical system of discs of unit thickness, right? These are actually aluminum cylinders, the aluminum, let's call them rods. We call them rods.
Okay.
And I have these because there were people doing research on the behavior of piles, structural engineering piles. You know what a pile is?
Oh yeah, the piles on the ground when building a
You have a surface, and then you have something like this.
Yeah.
And that's called a pile. Okay. And if you apply a load to this, for example, that, right? It resists because, it goes in compression on this side. It's all complicated, right? And if you want to study this, you can do it in sand in the laboratory, or you can take this. Whoops. Let's get the view to be the fit to the window. People did a study of this by not using sand, using these. They took these rods and they put them together so they perfectly lined up, and they put them between two sheets of plexiglass of glass. You could see them. And so their model was a physical model made up of a bunch of those unit thickness. Whoops, going too fast. Right? Get rid of this. I think you get the idea. Right? Right? So they had a whole bunch of discs like this that were packed together, and then they had a pile in there, and then they loaded it. And what they could do is they could look at how these discs move when the pile is loaded.
Yeah.
Okay. And they studied things like different size distribution of these. This is like a two-dimensional version of sand with a pile. Okay.
Okay.
And they did all sorts of experiments on this system in the real laboratory to try to make a simplified system of sand. And this is very simplified, right? Because the loading is just these cylinders going this direction. And in a real system, there's load going out of plane.
Yeah.
Right? And so it's a very, very poor thing, right? But that's what they did. And like this thing was not a disc. This thing was actually a big, if you think about this thing was actually like this. This thing was this, because these things got a unit thickness, and then there's a glass plate on the front and the back. And so this thing was a big giant sheet. and then they loaded that thing, right? Because it has to go through all the way because it's
Mhm.
just a uniform symmetric thing. So this is important to realize because the PFC2D model is this. It is not spheres.
Mhm.
And this is very misleading. Most people, I think, who see discrete element models look at 2D
Mhm.
models. Most papers are written with 2D models, and they
Okay.
look as if they were sand, and you see force chains and all this other stuff, but it's not actually the true physics of spheres,
Yeah.
or it's this. And so
Mhm.
any result in a PFC 2D model needs to be interpreted as if it was a weird test on these unit thickness rods that are cemented, maybe cemented together. Okay.
Mhm.
So this is an important thing of this. So this is what the 2D model is, and it's always unit thickness. Okay. So
Okay.
now let's talk about the basic physics of what happens when two particles touch. Okay. They start to
Mhm.
touch. Now, what the heck happens if I force them to touch and I keep making them move more together? What happens? So we're going to talk about the fact that the particles are going to begin to overlap. Okay.
Mhm.
And
Okay.
because they're overlapping, we call this a soft contact. Okay. So what do
Okay.
we mean by this? So here's two tennis balls sitting on my
Mhm.
desk. Let's pretend these were the tennis balls now, and they're perfectly
Mhm.
lined up. They're just touching, no force.
Mhm. Mhm.
And there's a steel plate here and a steel plate here. This one can't move. This is the initial system. And this steel plate, and again, there's no overlap. They're just barely touching. Okay.
Okay.
Now, let's force this plate to move down. And so the way we're going to do it, because I'm a showman, remember, is I am going to
Mhm.
stand on this and I have perfect balance. Okay. So here I am.
Okay.
That's me. That's what I look like.
Mhm.
And I'm going to stand on there. I have a certain mass, hit it with gravity.
Mhm.
That's the weight of me, which it turns out to be a force. It's acting on this steel platen. The force makes it go down by delta, right? And if these
Yep.
things don't break, it's going to go down by delta and stop, and everything will be in equilibrium. You agree?
Mhm. Yep.
That's what's going to happen. And if these are tennis balls, they're going to do this, right? They're going to squeeze down and they're going to bulge out. These dots
Mhm.
are where the
Yeah.
initial
Oh,
system
yeah.
is.
Yep.
Make sense? You
Yeah. Yeah.
kind of
Yeah.
can see it here. Okay.
Yeah.
So do you agree? This is what it would look like if these were tennis balls. They
Yeah.
would,
I agree
and
with
there
that.
would not be overlap,
Yeah.
right? They would just squeeze and you would get a flat surface developing here. And you would
Yeah.
get two flat surfaces developing here. And in 3D,
Yeah.
this would be a disk. And there would be a disk of surface touching that's flat.
Yeah.
And the
Yeah.
more you push down, the bigger this radius would get. Okay.
Yeah. Mhm.
Okay. So this is
Yeah.
what would happen if we had real deformable material. Notice this is not rigid. This shape has changed.
Yep.
Okay. And if you think
Okay.
about it, the way that it changes will be related to the constitutive behavior. So if this is most materials given a small strain behave as linear elastic isotropic material. And such
Mhm.
material is characterized by Young modulus and Poisson ratio.
Mhm.
Okay. So
Okay.
a good approximation for very small strain for all materials under small
Mhm.
strain, they're going to be linear elastic isotropic, which means they're going to do this. Okay. If you
Yeah.
solved using something called theory of elasticity, if you use
Mhm.
that theory, you could solve the problem of two spheres that were with an applied displacement. What would be their shape, their final shape, and what would be, now there's going to be traction acting here
Mhm.
against them. Okay, you could solve that problem. And if you solve that problem, you would get this shape. You would get
Yeah.
a straight line disc that would form, okay?
Okay.
And the solution to that problem is going to be controlled by the Young's modulus and Poisson ratio of this body and a different Young's modulus Poisson ratio of this body and the radius of the top two bodies. Because that would be a solution for given two bodies, two surfaces pushed against each other, what shape do they form? And the way you describe the shape of a surface is called radius of curvature. Any shape, if you go locally, can be described by a radius. But that radius of curvature is going to change in general for a general shape. Okay. So this is a problem that could be solved. And there's a guy who solved this in 1887, I believe. His name was Hertz. And he solved the problem of theory of elasticity of two elastic bodies pushed together and showed that they did this. Just keep that in the back of your head for now. This is what would happen in reality. Now, in the discrete element model, though, remember, we're going to say the particles are rigid, so they're going to have to overlap. In order for this to move down, which is the boundary condition, it's going to move down. I'm going to force it to move down. What's going to happen to these particles? Well, they're going to keep their size and shape, but they're going to get pushed down. And there's going to be overlap. So watch. Boom. Here we go. This radius and shape is exactly the same. Okay. However, to accommodate the motion of this thing, we have to allow overlap to develop. And so if you take the sum of the diameters and you subtract off all three of these overlaps, you get delta. Okay. So the particles, so this is what we call soft contact. The particles are going to overlap and all of the deformation. So there's an imposed deformation of delta over the entire system. All of that deformation consists of overlap at contacts. Okay. In a real system, there is actually going to be some craziness happening here, but it's going to be really small. And most of the deformation is the contraction of the bodies because the bodies are deformable. Okay. If we don't allow them to deform, well, the only choice we have is to allow the contacts to overlap. And that's what happens here. Okay. So this is what's happening at all the contacts overlap. And we're going to find out that for this approximation of behavior to make sense, this overlap should be relatively small compared to the radius of the two particles.
Of course.
If this overlap reaches the radius, this entire approximation gets weird. Okay. So in most discrete element simulations, these overlaps are quite small, maybe certainly less than 5% or 10% of the radius. Okay. So keep that in mind as well. Now, how good of an approximation is this? If we had quartz sand, this is actually quartz sand. And you can see it's crazy. It's angular. It's a freaking mess. Okay. This is a typical sand. You can see the length scale, pretty small sand, but you could still see that if you held it in your hand. You could see these things. If you squeeze this together, the quartz sand, you're applying delta, right? And where does the delta go in this system? Most of it goes in rearranging these guys. And they rearrange, and there's just a relatively small amount of each of these grains deforming. Okay. And so, and the other thing to understand is if you actually have two surfaces of two bodies and you squeeze them, there is a amount of stiffness, you can call it. There is like overlap here. Okay. And this is a measurable thing. If we have, for example, in the laboratory,
Mhm.
especially in the rock mechanics laboratory. We have a hunk of rock, okay?
Mhm.
And what we can do is we can cut it 2 pieces,
Mhm.
okay? So now we
Yeah.
have 2 separate pieces, and we call this a joint,
Okay.
okay?
Yeah.
We call this a joint,
Yeah.
okay? And these 2 surfaces, what you can then do is you can take force this one to move down, don't let this
Mhm.
move, and you will
Mhm.
measure force displacement of this.
Mhm.
And you will find that for a rock, there's very small amount of displacement of this thing changing shape, but there's quite a bit of displacement at these 2 surfaces, okay?
Yeah.
And so we call this a joint stiffness, and this is a
Okay.
measurable thing. And this is happening because if this is the joint, here's the one side,
Mhm.
here's the other side, right?
Mhm. Yeah.
And so, just a second, watch this. And now let's rotate this guy 90 degrees. Boom. Oh, got to rotate it more. Rotate another 90 degrees. There we go, right?
Mhm.
Now, this is your picture in your head of a joint. And you say, well, what the
Yeah.
hell? How can it have stiffness? But if you recall from the picture of the 2 grains of sand that were
Mhm.
pushed together, they're not perfectly, they're not like this. So the
Yeah.
real surface, if you zoom in on it, is filled with all kinds of asperities,
Yeah.
right? And
Yeah. Of
so
course.
this is real, and I can show you all sorts of, when you take your scanning electron microscopes and you zoom into a rock joint, it's made of all these asperities. And
Mhm.
so you have 2 of these things,
Mhm.
2 surfaces with asperities, and they might look like this. And even if you cut this with the saw, you tear
Mhm.
it up and it produces this. It just depends on what the length scale is. And it's
Okay.
these asperities, when they push together, that are deforming. And it's totally
Mhm.
local. It's this region where all the deformation is happening. It's not the
Mhm.
deformation. Hardly anything is happening out here. And so
Mhm.
this is what we are capturing in a soft contact approach. Okay.
Mhm.
We don't model this weird shape. We just model a straight line, but we allow it to overlap. Okay.
Okay.
Because
Okay.
that's actually what happens here. This
Okay.
thing, when it moves, starts to overlap with that thing. And these things start
Mhm.
breaking and all kinds of nasty stuff happens here. Okay. With these
Mhm.
asperities. And so there really is a measurable stiffness and a measurable displacement locally, a measurable overlap. If you just talk about this surface relative, this theoretical surface relative to the other one, they actually overlap each other in a
Okay.
real joint. And do you
Mhm.
see why? Because in a real joint, that's not the surface. Okay.
Yeah.
So this, going back to this soft contact thing, this is what's happening largely here. So this approximation is quite good for
Mhm.
something like a quartz sand, like a dry quartz sand. I say dry because if it's dry, there's no stickiness. And so there's only forces that can happen here. Okay.
Mhm.
Now,
Okay.
if instead the particles, do you know what marshmallow is? You eat these?
Oh, yeah,
Marshmallow.
yeah. Okay, okay. I know that.
Okay. You eat
Mm-hmm.
these and they're
Yeah,
very,
yeah.
very soft. You can squeeze them with your fingers. So
Yeah.
if you push together a pile of these,
Mm-hmm.
most of the deformation is happening in here, not
Yeah.
here. Okay.
Yeah.
So that's why I say it's a good model for this. It's not a good model
Mhm.
for this.
Okay.
Okay.
I got
So
it.
does that make sense? So if you were modeling
Yeah, of course.
marshmallows, but hold on, this is gonna blow your mind.
Mm-hmm.
If you wanted to model marshmallows with a
Mm-hmm.
discrete element model, well,
Mm-hmm.
so far all that I've said is every marshmallow could not be a single particle. Because if every marshmallow was a single particle, the particles don't deform.
Okay, so I can divide it into many particles, and then it can be.
Yes, you're so smart. Yes, you got it. That's exactly right. If we took an assembly of rigid particles with cement between them, now the cement has deformability. They overlap a little. And now the overall system, if you had 100 of them here, it would deform, right? And it would actually form, it would form this shape.
Yeah.
Okay. So we are here talking about the most fundamental level of the discrete element. At the fundamental level, there's only two particles and they're rigid. And this is what happens. Okay. So with me?
Yeah.
Okay, this is fun. Now watch. All that we've talked about so far is overlap. But in this system, well, there's a force. So there has to, in the end, there has to be a force, the same force here. And somewhere here, there better be the same equal and opposite force. Because for this to be an equilibrium, there has to be force here, here, and here, right?
Yeah, of course.
They all have to equal F. So how then do we obtain a force based on an overlap? So what we do is we introduce the concept of a stiffness. And so we can think of a stiffness, a way of visualizing it and physically understanding it is a spring, right? See, I'm trying to draw a spring here. And so the spring, what we're going to do is we're going to say every time there's a contact, conceptually, we're going to put in a spring. Because the spring gives you a relationship between force and overlap.
Okay, yeah, of course.
And so if you know, remember, everything that's happening here is motion. So we force a change in overlap, and we use the spring to compute the change in force. Okay. So this system started off with zero contacts. They were not overlapping. I forced this to move. As soon as one time step occurs, there's an overlap here, nowhere else. Boom, a contact forms. Boom, a spring gets put in. Oh, based on the delta, I get a force. I apply a force. The next time step, this guy has a resultant force. This guy moves. Oh, contact forms. There's a force. You can see how this is going to happen here. Okay. So there's springs happening here. Okay. They have a stiffness. Now let's go the next step. We have, again, it's motion. It's the motion that's happening. So there's a relative displacement. Why do I use the word relative? I mean, there's a displacement of this surface relative to that surface. So to make it clear, I'm going to use a particle and a wall. This is a wall. This is a surface. In PFC, a wall is a surface. So this particle started not touching. It was just perfectly lined up. It's dotted. I then impose a motion. Now there's overlap. That overlap is delta. And that overlap produces a force because of the whatever contact model. And the contact model we're going to describe is a linear contact model, which means it has a spring of a certain stiffness. So look what I'm plotting here. This x-axis is going to be this delta. And I'm going to plot it such that I'm going to plot negative delta. So negative delta would be moving up. So negative delta means there's a gap there. It's not overlapping. And if it's not overlapping, the force is zero. And I put a line like an arrowhead here because I mean anywhere here. It's going to go forward or backwards. You could keep moving it any way you want. If there's a gap there, there's no force. Now,
I got it.
I make it go over this. Now suddenly, I'm going to produce a force. And notice this axis is tension. This axis is compression. So when they start to overlap, compression starts to happen, right? And compression means the forces are pushing against each surface. And the relationship between that force and that displacement is going to be linear, and that's going to be given by the stiffness of the spring. This is the simplest possible spring, a linear spring. So no matter how much you push it, it just builds up a force like this. And in the discrete element model, locally, this just goes forever. If you keep pushing him and the overlap gets bigger and bigger and bigger, the force just gets bigger and bigger and bigger. And eventually it gets so big that this overlap is as big as the radius of the particle. And then things don't make sense anymore. And in that case, PFC just removes the contact. It doesn't make sense. Okay. This has nothing to do with breakage yet or anything. So the particle never breaks. It just keeps getting pushed more and more. And it cannot take tension. Okay.
Okay.
Now, while we're here, we got 10 minutes here. Let's describe this business about, this is what we call the linear model. And we're going to find out that it's going to actually have a normal stiffness, which we're showing here. It's normal to the surface, but it also, if I take this particle and move it to the right, there's going to be a relative shear motion. And there's going to also be a spring there, and that's going to be called a shear spring. So it's going to have a normal stiffness and a shear stiffness.
Okay.
That might not be the same, but let's not worry about that yet. Okay.
Okay.
For the linear model, for the simplest case of pushing them directly together, this is the only thing that happens. Okay. So it's got a parameter and it goes like this. Now, if you were to actually take tennis balls, which are deformable bodies, and if you were to impose a small delta to it, they would form this shape. Okay. And if you measured how the force is related to the delta, what you would find is it would look like this. The slope of this is the stiffness. And notice the slope gets bigger, 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 bigger. That means that in a real system, this is what it looks like. If you start squeezing those tennis balls together, when you first, and you can actually feel this, if you just take them and hold them in your hand and slowly move your hands together, at the beginning, there's not much force required. But as you keep moving them, it gets stiffer and stiffer. This actually happens. Okay.
Yeah.
Okay. This is computable. Again, in 1882, Hertz solved the problem of two elastic bodies pressed together. Okay.
Okay.
And this is also in PFC, and this is called a Hertzian contact model. Hertzian model. Okay. It's going to turn out that in the world of bonded particle modeling, we don't typically care about this, and we use this model.
Okay.
And what we're going to do when we bond them is now when they pull apart, the force is going to build up. Because now tension is going to be able to get carried there if there's bonding. Okay. The Hertzian model is, though, used often in people doing granular systems. Like if you have the coffee bean thing and you fill the coffee bean grinder and you want to see how it flows if I open up the bottom or something, or if you want to mix material and you want to see how the patterns form in things, people will often use a Hertzian contact model instead of a linear model. Okay. And we're going to find out, I don't know if I show, we'll talk about this later. This Hertzian model now does not have, the parameter is not a stiffness. The parameter here is going to be the Young's modulus and Poisson ratio of particle 1 and the Young's modulus and Poisson ratio of particle 2. And the local radius of curvature of particle 1 and particle 2. Because that's what has to be considered if you want to do two elastic surfaces pushed together. Okay. So that would be a different set of properties. In PFC, it's trivial. It's going to be a way to tell it when a contact forms, I want you to put in the linear model. And I want you to use these values for its parameters. Well, you can just as easily tell PFC when a contact forms, put in a Hertzian model and use these parameters. Okay. So we can do all of that. We're going to pretty much always work with the linear model, and it's sufficient for the vast majority of simulations. Okay. Okay. 5 minutes. Let's cover this. This should be fun. Well, hold on. I think we're going to stop actually. Okay. And I'm just going to I'm going to show you this slide, and there's a lot more coming, but I think this will be a fun slide to stop with. Okay.
Okay.
We're going to come up with the 2 and only 2 equations that are ever used in distinct elements. It's so simple. And we're going to show the 2 people who developed those equations. Okay.
Okay.
And so in the distinct element method, what are we going to do? Go around this once as one time step. Take a time step. Go around this. This is the algorithm. Let's see what this algorithm is. You have a collection of particles. They're packed together. Now, you go to each particle. What do? You sum up all the forces acting on it. Remember, there's contact forces. And there might be moments at those contacts. So you solve that. You say, there's a rigid body. It's loaded on its boundary. You take all the force. You take the total force sum. And you do the law of motion. You do F equals ma. Okay?
Okay.
And then that lets you figure out how to update the positions of these things. And we'll work that out. Okay? And so then you update the particle positions. They all move. And the walls move. And when you do that, there might be new contacts that form.
Yeah.
Okay? Now, what do you do with the contacts? Now we have to apply the stiffness. So we have to figure out what the force happens. So let's call this a force displacement law. And so at the contact, you have relative motion. And you have some kind of constitutive law, a linear model. Okay? And that lets you update the forces. So now you update all the forces. Now we're done. Because now we go back to the particles and we sum up all the forces. And we keep doing this. Now we're going to unpack this more, but let's say this is based upon, I'm going to say, on the shoulders of giants, right? This is how science works. Somebody figures something out, and then you start with that, and you figure out some more, and then you start with that. So we're starting with one of the giants of mechanics, Isaac Newton. And he came up and showed us that we have this force equals mass times acceleration. Notice these are vectors. This is a vector equation, right? So 1687, Newton did this. Then, for the force displacement law, we have someone named Robert Hooke, who was an Englishman. And he was even earlier, 1678, before Newton published. And he came up with this equation. Force equals stiffness times overlap.
Yeah.
Let's look at this. So Newton published all of his work in this thing called the Principia. Okay, this was this amazing giant thing. This is the basis of all mechanics. Everything came from this. Okay. And what's cool about this is I know quite a bit about the life of Isaac Newton. And he was a very curious person. Remember I said the best researchers are fundamentally curious? And they also really like what they do because it's fun. So look at this. I'm going to show you a quote of what Isaac Newton himself wrote. Now, he wrote this towards the end of his life. Okay. At the end of his life, he was very famous at that point already. Okay. And so here's this very famous guy, and he's writing a little bit about, you know, what was it like in my life doing this? Because many people were like, oh my God, you're like a god. Like you figured this stuff out. This is amazing. Here's his quote. He says, I do not know what I may appear to the world, so I don't know what people think of me, but to myself, I seem to have been only like a boy playing on the seashore and diverting myself, and now and then finding a smoother pebble or a prettier shell than ordinary, while the great ocean of truth lay all undiscovered before me. I completely love this thing, right? So to him, he's this, pretend you were out having a coffee with Isaac Newton and you say, oh my God, what do you think of, how did you figure out all this stuff? And he says, oh, it really wasn't that much of a big deal. I feel like it was fun. I was just on the seashore, right? And all I was doing was being curious. Oh, I found a pebble. Isn't that cool? And you guys think that I've solved everything, but it's just the beginning, right? The great ocean of truth, right? And just think, we've had like almost 350 years since this time, and we still keep figuring out new stuff, right?
Yeah.
So that's what we need to remember about Newton. Now, what about Hooke? So Hooke came up with this force displacement law. Now, let's talk about this. This 1678, he wrote a paper as well. Okay. And back then, all the papers in the Western world were written in Latin. Okay. The language of Latin.
Yeah.
And that's why it's got this crazy word, crazy title. But what does it mean? If you translate this into English, it basically says this is a paper about a thing called a spring. Okay? And here's a spring. This is in the paper. This is a figure in the frickin' paper. Okay? Here's a spring. And what did he do? He took a spring, he hooked it onto the ceiling, he took a dish and put it on the bottom. Okay? And he measured. He put some measure here. So there's the 0 point. And then he went and he put some sand in here that he knew how much it weighed. And he measured the delta. And then he went and he put double the amount of sand and he measured the delta. And he found that there was a linear relationship. If he doubled the amount of sand, he doubled the delta. If he tripled the amount of sand, he tripled the delta. Okay.
Yeah.
So these were experiments he did. So he was experimenting. So look what he said. This is the key point. He didn't. So you could say, oh, that's cool. So this spring, which is some weird thing that we use in machines that we're starting to build in England, we could make these springs now. He said, oh, good. So the spring, that's fine. It applies to a spring. That's all it applies to. Well, wait a minute. This was the key thing. He said, no. This actually applies to everything, to all bodies. Now, how did he know this? He did experiments. Okay. He went and took other materials, like he took a stone and he squeezed it and he measured force displacement and he found it was linear. He took other things. Here we go. Wood, metal, stone, hair. He took hair. Remember we talked about hair. Pulled out your hair, measured stretched it, right?
Yeah.
He did all these experiments, okay? And he says that in every, and he didn't know what to call it. They didn't have a concept of an elastic body because elasticity didn't exist. He just called it a springing body, right? And this is a linear spring. The force to restore itself is proportional to the distance. F equals K delta, right? And so this was F equals K delta. And he made this key observation, and then he did experiments and showed for all these different things that it held, right? And so this then is what we now call Hooke's law. And it's Hooke's law. Deformation is linear related to force. That's the foundation of everything else in the mechanics of elastic bodies. Notice the mechanics of rigid bodies came from Newton. Newton never considered that his bodies could deform and change shape. He did rigid bodies. Hooke then came along and talked about the forces that develop and this idea that bodies can change shape, right? And so if you put those two together, this is what you come up with. You come up with this relationship. Rigid things move, but then when they start to overlap, forces develop. And so you can this is the basis. Everything follows from that. So I used to joke, but I'm actually serious. In the time of Newton in 1687, Hooke's work had already been done. Okay. Everything was there. If Newton had had a computer available, it's very likely that he would have taken this and he would have done what we're doing now.
I think so.
Okay. So this is like super cool, I think, actually. So this is what I want to leave us with. And then we're going to continue to unpack this kind of stuff in terms of how it's done in PFC.
Okay.